Hi everyone, this is Mrs. J, and today we are going to be factoring polynomials. But first, please pause the video and give the warm-up a try. All right, go ahead and check. For both of these, make sure you have that 0 placeholder for your x squared term, because you'll notice we go 4, 3, and then 1. So you need that 0 placeholder. Either way, you should end up with the same answer. So here's the long division process. Here's the synthetic division process. So make sure you check your work and make sure you're comfortable with both methods for dividing polynomials. Okay, today we're going to be factoring polynomials. So a lot of these methods we already know because we know how to factor quadratics, which are just a type of polynomial. So if you look at the ones we already know to check for a GCF first. We know magic x is a method we can use for a quadratic trinomial where a equals 1. We know the bottom up method, which is for quadratic trinomials where a is greater than 1. And we also know difference of two squares, which are expressions in the form of a squared minus b squared, and it just factors out to this. Today, we're also going to be looking at quadratic type polynomials. So polynomials that aren't quadratic, but you can factor them like a quadratic. We're also going to learn a new set of formulas for the sum and difference of cubes. It's kind of like difference of two squares. It's a specific scenario that has a formula that helps us to factor it. And then we're also going to talk about grouping, which is a method we will use to factor polynomials with 4 terms. So if you look, over half of the methods that we use for factoring polynomials, we already know how to do. So it's just a couple new ones, and then we should be able to factor just about anything that we come across. All right, let's give a couple of these a try together. So for part A, remember the first thing we always check for is a GCF, which this expression has. All of the terms can be divided by x, so that's going to be our GCF. Make sure it doesn't disappear. This is not an equation. Regardless, we would never divide both sides by x anyways. You have to factor it out. It needs to go out front. It is a factor. It's the greatest common factor, so we need to include it in every step of our work. Then we look at our remaining expression and we ask ourselves, can I factor this more? Well, this is a quadratic trinomial whose a value is 1. So I'm wondering, are there two numbers that multiply to make -5 and add to make -4? Yes, -5 and +1. So we have x times x minus 5 times x plus 1. So please don't forget about that factor of x out front. We have 3 factors for this problem. All right, let's look at this next one. So same thing, I'm always checking for a GCF first. So I notice this case, both terms are divisible by 3. And then the largest degree I can divide out of both would actually be x cubed. So you're always going to pick the smaller of the 2 degrees, and that will be your greatest common factor because it has to work for both. So I'm going to divide both terms by 3x cubed. Make sure I put it out front. And what I'm left with is x squared minus 16. And again, I'm going to look and say, can I factor this more? And I notice, okay, it's 2 terms. I'm subtracting. They're both perfect squares. Oh, this is just difference of 2 squares. Where my a value is x, my b value is 4. So I have 3x squared times x plus 4 times x minus 4. And there you go, fully factored. All right, now let's look at this one here. We always, again, check for a GCF first. I notice all of the terms are divisible by 5. That's the largest thing I can divide into all 3. And then I notice that my smallest degree for x is x squared, so degree of 2. So that's going to be the biggest thing I can divide out of all 3, because again, it has to work for every single term. So 5x squared is my GCF. Make sure to place it out front. It is a factor. And I'm left with x squared plus 6x plus 9. And again, I'm going to ask myself, can I factor more? Here we have a magic x scenario. What multiplies to make 9 and adds to make 6? Well, 3 and 3. So we have 5x squared times x plus 3 times x plus 3, which is completely fine to leave your answer like this, or we could say 5x squared times x plus 3 squared. Either way is completely fine, completely correct. So you can see that even though these are not quadratic equations, we still knew all of the techniques of factoring that we needed for these polynomials. So a lot of the stuff that we learned in the previous chapter carries on to this chapter. Alrighty, so now I'm going to ask you to pause the video and give these two a try on your own. Okay, go ahead and check your work here. Both of these problems have a GCF that you can factor out first, and then you can factor more either using magic x or difference of two squares. All right, so now we're going to learn a new method for factoring. There are actually two. It's the sum and difference of cubes. So again, this is kind of like the difference of two squares. It works for very specific cases, and there's a formula that we use. So the first is sum of two cubes. So again, if you see that you have two terms and you're adding and they're both perfect cubes, you're going to look at the terms. If this is a cubed, you could take the cube root to find a. If this is b cubed, take the cube root to find b. And we just simply substitute those a and b values into this formula. A plus b times a squared minus a times b plus b squared. So you'll notice for the sum formula, the first binomial has a plus sign, but the second sign is a minus. Now there's also a difference of two cubes. I do want to point out that while there is a difference of two squares, there's no such thing as sum of two squares, but for the cubes, there's both. There's a sum and a difference. So kind of same idea, if you have two terms, but you're subtracting and they're both perfect cubes, you find the a and b values and you substitute it into this formula. The formula is the same except for these two signs are swapped. The first term is now a minus sign, and this is now a plus sign. So the first sign matches, the second sign is always opposite, and the third sign is always a plus sign. So for this, it's really important that we're able to recognize perfect cubes. So you see a number, you say, oh, I know that that number is just 4 cubed. So let's list out some perfect cubes. Well, the first one is going to be 1 cubed, which is 1. So we have 1. 2 cubed is 8. 3 cubed is 27. 4 cubed is 64. So 64 is kind of interesting because it's a perfect square and a perfect cube. 5 cubed is 125. 6 cubed is 216. 7 cubed is 343. 8 cubed is 512, 9 cubed is 729, and 10 cubed is 1,000. So again, it would be useful to start memorizing these terms just so you recognize them. Like if you see the number 343, you immediately think, oh, that's 7 cubed. So the first 5 we see a lot. So definitely make sure you know the first 5. But beyond that, it's just useful to recognize them. I guess you can always check to see if it is a perfect cube in your calculator, but it's nice to recognize 216, 343, 512, 729, and 1,000 as perfect cubes. Okay, let's give this a try. So I look at it and I say, okay, there's two terms I'm subtracting and they are both perfect cubes. So first thing I'm going to do is I'm going to list out my a and b values. If x cubed is a, that means that a is just x. This is my b cubed term, so I say, well, what's the cube root of 125? And that'd be 5. And then I'd like everyone to do this. We're going to actually write out the formula. The more you write out the formula, the easier it will be to memorize. So a minus b times a squared plus ab plus b squared. So now we're simply substituting values in. 5, or x minus 5, a minus b, times a squared, so x squared, plus a times b, so 5x, plus b squared, and 5 squared is 25. And this should be fully factored. As long as you checked for a GCF first, the remaining factors should be unfactorable. So like this trinomial, you should never be able to factor it more if you did it correctly. Okay, let's look at this one. There's no GCF, but I do notice that there are two terms. Everything is a perfect cube, and I'm adding. So this is going to be the sum of two cubes. So here, the cube root of 8 is 2, so our a value is 2x. The cube root of 27 is 3. And our formula, let's all write it out together, a plus b times a squared minus ab plus b squared. So remember, for the sum, it's a plus here, but a minus here. So it's swapped from the difference formula. Then we're just substituting. So we have 2x plus 3 times, now this is the tricky part where I see a lot of mistakes. When I do a squared, a lot of people forget to square the 2 and the x. So it's actually 4x squared minus, well, 2x times 3 is 6x, and then 3 squared is 9. And again, as long as you checked for a GCF first, if you're using these formulas, they should be completely factored once you've used it. All right, go ahead and pause the video and see if you can give these two a try on your own. All right, go ahead and check your work here. I do want to point out that when you're listing A and B are always positive, just like when you're using difference of two squares. And then I really would like to see you guys writing the formula out and then simply substituting the a and b values. Be careful with this step again. If you're squaring your entire a term, you have to square the 3 and the x to get 9x squared. All right, so now we're going to learn another new method, which is called factoring by grouping. So for this one, you'll know to try to factor by grouping if you have a polynomial with 4 terms. So if you have 4 terms, just try it. First, check for an overall GCF. This problem doesn't have one. So if you see, again, you have 4 terms, what you're going to do is you're going to imagine that you're just grouping the first 2 terms together and then just the second 2 terms together. And you're going to look for a GCF within the first 2 individually and the second 2 separately. So I look at x cubed and 5x squared, and I see that the GCF is x squared. So I'm just factoring it out of the first 2. So I have x squared times x plus 5. Then I'm going to look in the next 2, and I say, oh, I have a GCF of negative 4. So I'm going to factor negative 4 out of both. And again, this negative does belong to the 4x squared, or the 4x. So I put minus 4 times, and I have positive x, and then plus 5. Now, if you do this and you notice that these 2 factors are the same, and again, it only works if these 2 factors are the same, then you can factor by grouping. You can actually take these 2 terms and combine them into their own factor. So it becomes x squared minus 4 times x plus 5, because each of these terms have to be distributed to x plus 5. Now, sometimes after you do this, you'll be done. Here, we have an interesting case where we can actually factor more. So hopefully we realize, oh, this is difference of 2 squares. So we have x plus 2 times x minus 2 times x plus 5. So sometimes after we factor by grouping, we can actually factor a little bit more. Sometimes you can't. All right, let's try another one. Here I see I have 4 terms. There's no GCF for all 4, so I'm going to try to factor by grouping. It's just something you should always try if you have 4 terms. Okay, so for the first 2, I notice that there's a GCF of 2x squared. So I have 2x squared times x plus 2. And then if you notice for the second 2 terms, there is no GCF. Let's treat it like a GCF of 1. And let's actually say plus 1 times x plus 2. I know usually we don't do that, but let me show you why. So again, we have this scenario where we have that same factor. We have x plus 2 for both. So when you go to group, you need to have a coefficient for each one. So that's why I like to write the plus 1 out front to remind me that I have something to group there. So the 2 terms that I'm grouping are 2x squared and positive 1. So I have 2x squared plus 1 times x plus 2. And then you check and you say, can I factor more? And in this case, you can't, which means we are done. So again, anytime you have a polynomial with 4 terms, you can always try to factor by grouping. Okay, go ahead and give these two a try on your own. All right, go ahead and check your work here. So again, group the first two and look for a GCF, group the second two and look for a GCF. And if these factors match, they do have to match, you can turn the two coefficients into their own factor. And for part A, you can actually factor a little more because x squared minus 9 can be factored more using difference of 2 squares. For part B, once you factor by grouping, you should be done. All right, the last type of factoring we're going to talk about are what we call quadratic type polynomials. So a quadratic type polynomial is a polynomial where the degree of your first term is double the degree of your middle term, and then your last term is a constant. So I understand this is not a quadratic, but we can factor it like a quadratic. So when you see this, maybe something you could try is just imagine it was a quadratic equation. Let's turn it into just x squared plus 5x plus 6. And you ask yourself, how would I factor this? Well, I'd factor this with magic x. So we have 3 and 2, which would give us x plus 3 times x plus 2. Now, if we have this and we foiled it out, right, x times x is just x squared. But we want x times x to be x to the 4th. So then all you need to do from here is you're essentially going to take this term and split it in half. So it becomes x squared plus 3 and x squared plus 2. So we're simply adjusting it to meet this higher degree. Okay, so if you multiply this out, we would get x squared times x squared, which is x to the 4th, plus 2x squared plus 3x squared, which is 5x squared, and then plus 6. So we can factor it like it's a quadratic, and then we just adjust the degree of our first term to be half of whatever this is. We should be done. We should always ask ourselves, can we factor more? But there's no way to factor these two factors, so we are done. Let's look at this next one. So again, I see that this degree is double this degree, and then we have a constant. So even though it's not a quadratic equation, it's a quadratic type equation. So I'm going to pretend for a second it just says this. And again, if I were to factor this, I would use magic x. What multiplies to make 8, positive 8, and adds to make negative 6, we would have negative 4 and negative 2. So that would factor into x minus 4 times x minus 2. But from here, remember, we need to adjust this first degree. So if we multiply this times this, we would get x to the 6th. So you're going to look up here, and we're essentially just going to divide it by 2, and that should be the degree in our factor. So we have x cubed minus 4 times x cubed minus 2, because x cubed times x cubed is x to the 6th. And then you could ask yourself, can I factor these more? But 4 and 2 are not perfect cubes, so we can't factor more with our difference of cubes, which means we are done. All right, let's look at this last one. So this is actually a different type of quadratic type equation. So this is not a trinomial, but if you look at what's going on here, I know it's not a quadratic equation, but this could still work for difference of 2 squares. I have 2 terms, okay, I'm subtracting, and everything is a perfect square. 16 is a perfect square, x to the 4th is a perfect square, and so is 81. So I'm going to use difference of 2 squares. So here, my a value is 4. Instead of just being 4x, it's 4x squared. And here my b value is just 9. Remember, my formula is a plus b times a minus b. So I can do 4x squared plus 9 times 4x squared minus 9. And then I should always check to see if I can factor a little bit more. This I cannot factor because there's no such thing as sum of two squares. But here, I can actually factor again using another round of difference of two squares. And here my a value is just 2x. My b value is 3. So we have 4x squared plus 9, our original factor. Then we have 2x plus 3 times 2x minus 3. So again, this is a different type of quadratic type equation. We factor with difference of two squares, just like a normal quadratic equation, but we just need to increase the degree of x. So again, anytime you have that trinomial where this exponent is double this exponent, like we have 4, 2, and then a constant, or we have 6, 3, and a constant, we can factor it like a quadratic and then adjust the exponent in our answer. All right, here is the last one for you to try on your own. Please pause the video and give it a try. All right, go ahead and check your work here. We do have that trinomial where this exponent is double this exponent, and then we have a constant. So this is a quadratic type polynomial. So we can factor it like a quadratic. So we would get x plus 8 times x minus 4, and then we just adjust this exponent to be half of the biggest one here. Now, this could be a little bit tricky. We're actually not done. You have to notice that, oh, x squared minus 4 can be factored more with difference of two squares. X squared plus 8, you can't factor more, so that factor will be the same. All right, that is all for today's video. Thank you so much for watching.